come, so they apologize very deeply, so have some personal issues. So don't worry, you still have class, so you teach. I hope I can do as good as them. So, but first for today, I want to make a short presentation. So I think it's a good introduction for the school. So I don't know if you will understand everything I will present, but I think at the end of the 2-week school, you will be able to understand everything and to read everything I will present. So you will see again what Annabelle just did, one example, but and plus some fraction topic, AI, how. So next week you will starting tomorrow you will start having machine learning for image processing. Next week we will have data analysis. So normally at the end of the year, at the end of the school, everything will be. So I have to tell you to try to enjoy this 2-week school because you will see this is the first day, but next week you will say it's already finished. So enjoy the school, talk together, talk with the lecturer. So my name is Mammeri, so I am a professor with Campbell Institute. So maybe you heard my Campbell doing your mathematical study. Or the same guy, or probably not the guy you know from the matrix, not the author from the matrix distribution. So if you are like a web page to communicate. Okay, so I will provide an example of what we see in the school, but in a very particular context. So the context of the head and neck cancers. But you need to do this kind of work, so I'm a mathematician. So actually my real background is in pure analysis. So if you read my thesis, there's only PDE, analysis, theory. Nothing else. So when you want to work on that, so you have seen the example of Annabelle, so it's difficult to do it as a only mathematician. So this is a joint work with the hospital, the University Hospital of Monnet, some medical doctors with the surgery also. So actually the problem coming from the surgery. And then we develop a model for a strange so with disease. So because we are expert in the surgery of this. So we will have a roundtable in the school and we'll talk about that, the interdisciplinarity in mathematics. So can you do good modeling, medicine, colors and mathematicians? So we are lucky, we are most of you are mathematicians, but we are also in the room medical doctor, people from pharmacy, people from biology. So it will be good thing to extend what you think about doing mathematics only for mathematics, which is something. But we can discuss later on. So what is the head and neck cancer? So this is, I will not make a class the disease of biology, not my job, I don't have time for that. So every cancer that develops on the face, and this is actually a common cancer, not the first one, but well-developed cancer. And why we work with this hospital? So before I was in this university, so because in this hospital were the very first face transplant in the world. So this hospital is very famous, so if you look at the website, the first face transplant in the world, this is in displayed by the lab. So what characterizes this tumor? So it's very heterogeneous, so we don't know very well how it works, and it's very aggressive, and you have a lot of mirrors. So the first thing they want to know is the relapse, so we don't talk about that. But one important thing, so they notice that in most of the case, most of the patients have common thrombosis. And the thrombosis is the second cause of death from the patient. So when they know by experiment, this is like that, but is it so the objective, this is also about type of micro. So this is exactly what I will show you. You start from a medical question. So here I will not repeat the medical question, but you start from the medical question, you get the data. So what you can do with the data? So first, you need to analyze the data. So first you need to clean the data. You know about that. You need to analyze the data, identify what is relevant in your data, if you can identify something. Once you identify what is the most expected, then we create a model, we try to explain that. Go back to the validation, exactly what I will show you again. So have data, you create a model, and you have to come back to the validation. So validation, and maybe you have to do it again. So we use our data, clinical data from the hospital, for example, and you repeat again to confirm your result. So this is exactly what we will do. So first we will collect the data, I will explain all of that. So we'll select what is interesting for us in terms of clinical things. So just to explain you, so the data we use, we have 92 clinical parameter, and so maybe as a mathematician you say, okay, 92, you study it. But what is good when you want to identify, you can no, I don't care about 92. So what I am interested is this 19 parameter. So in this 19 parameter, we are not chosen by the mathematician, but we are chosen by the medical doctors. Okay, this is interesting. This is okay, so we extract from this clinical. So now you have to make all the pre-processing. So be careful when you use raw data coming from biology. So usually make use the data as they collected. So you have to make the process to clean everything. So sometimes it's very complicated, especially if you don't understand what are the data. So you are coming from medicine, you are doing mathematics, and you have to clean the data. Okay, and then we don't consider everything. We look what is interesting for the clinical parameter and select different. Yeah, we show you have a lot of. Okay, and then we will run our vaccine to say, okay, can you see something from my data? Okay, what I want at the end is tell me what is the most influence for my clinical. Okay. So I will not give all the details of that, so, but I will propose a mini project how you can collect data from the TCGA. So this is the Cancer General Attacks. So this is a database mainly from the US patients, where you have many data for many cancers. So you go to the website, write what you are interested in, and you provide you what you are asking for. So, but this is US data, so we are in France, so it's not exactly, you are in US exactly, but you can give you something. So, okay, so you see there are 587 clinical data, and for each patient, there are the gene, the protein, and the mutation. So I will not go today about the mutation and protein. We focus only on it. So 20,000 multiplied by 500. So you can start to say you have big data. So big data you can calculate. Okay, and so first, as I said in the beginning, we don't know very well what happened. So when you don't know what happened in the cancer, okay, so we start with what we call non-supervised machine learning. So next week you have a class on data analysis. So you say non-supervised, you give the data to the AI and you say, try to find something. what? Have a look. So you run like that, and just to confirm, then we do the opposite. So now you say, okay, this is important. So now I want to add to supervised learning. I would say, try to look in the data if you can find this or this part. So and what is very good? So from all these genes, at the end, we select 34 genes. It looks nice. So just to do the list. Okay, so if you are a medical doctor, so it was also very nice when you want. So when I see that, okay, I don't know what it was. So maybe someone knows. Some message, the medical doctor are working with it, he say, oh yeah, this is. But definitely, there are tools to translate that. So one tool, one very nice tool, is the gene card on the website. You put the list of the gene, you click, and it tells you what is the, so maybe I put too much, what is related. So this gene, so finally it's reduced actually up to 34, but there is some copy of the same gene. So you can reduce to 19, actually from the 1947 away. But this work also, you can use that, but this work to reduce 19 to 7 is also done with the medical doctor. Because if we tell you, this actually is the same as the other one, this we cannot measure, so we don't care. So it will help you to select. The final selection is done not by the machine, so even with artificial intelligence is very smart, because it reduces a lot. But at the end, the medical doctor said, yeah, this one is interesting, this one is interesting. And what is very interesting is that everything is related with what we call the coagulation. So this is the coagulation, so coagulation, the fact to make aggregates and release regularly. So I told you in the beginning what we know from the surgery is that the thrombosis is something very important. And you obtain exactly this. So when I start to work on that, I say I don't want to know what you know about the thing. We'll try. Let's see if the machine can say something. And what is very interesting is that they were right from the very beginning. But the question is, can I stop with this? Actually, it's an interesting result. Very good or not. But is it enough to say, okay, I know, I understand it? So this is why we have this class also on the modeling part. So the data say this is good, but why this is the coagulation? So now we need to provide explanation. And to provide explanation, we need descriptive. So I don't know if you heard about that. This is something very interesting. So the FDA and a little bit after the European Medicine Council, so they put in the recommendation. So it's still the recommendation, but strongly recommended. It means so if you don't put that in your clinical trial, it will be rejected. So there is no law. It's just encouragement that. But if you don't do it, you will be rejected, so don't know if you can. So in silico trial, so also just talk before you heard about that. So in silico trial, you will replace your animal, your in vivo, in vitro, by the computer. But what is important is the rule. So now in US, or very recently, it is approved. So you can make the clinical trial with only in silico cells. But what they say? So they say, for example, machine learning. So what I did before is not allowed. So if you use data and you make your machine learning and the machine the artificial intelligence. This is that. You cannot make a choice. Okay? It's not enough. It's even forbidden. If you say, I will use only the data, we'll say no. So you have to use, it's written there, physics-based, mechanistic, so as per principle, this is the mass that you know you have to use. So if you develop a model with that, okay, you can present the chart. Okay, you see, it's a very, very recent publication from the agency. So in US lab, a lot of in the future. But what I did before is very interesting, but it's nothing. So I have to develop something. So I will go very fast. So I need to explain the coagulation, the coagulant. I need to explain the coagulation and the fragmentation. So I know there is two students working on coagulation and fragmentation, and much more from that. I know that because one was in my lab for several months. so you have to explain what happened. So but make it simple. So what is the coagulation process? So we have the injury and the coagulation will start. So first thing, so you have the tissue factor, so some gene, so before you were very careful with my tongue, you have the F3. So this is the gene that regulates the growth, the tissue factor. So we will activate the coagulation process to make some and then we will start to make the growth. So you have different ways of explaining all of that. So you have some factor, some gene will be activated and it will start to coagulate. Okay, so create an aggregation. And then it will stabilize. And when it's finished, normally you have to break the aggregates. So this is the fulminants. So you have to take into account all of this. So to make it a little bit simpler. So this is actually the compartmental model you have seen before. So little bit nice aggregates, fulminants. But this is actually the compartmental. As you have seen before, with your compartment. And then you have to translate this into equation. So you can translate all the biochemical law as you did before. Then you put all the equation, you make some abstraction, and at the end you tell this kind of system of equation. Okay, but this is mainly what you have seen before, because it was chemical process, not exactly the same. Okay, so you have this system of equation, but it doesn't give the aggregation. But then you can complete the aggregation. So next week I will make a short lecture on the aggregation model, so I will explain it before. But it's quite easy. So to compute an aggregate of size I plus G, what you say is something of size I plus something of size G. So when they put together, it's I plus G. So and you have the coagulation process and the degradation process. So this is not exactly a chemical process of coagulation and fragmentation. So at the end, you have a system of differential equations. So normally it's an infinite system of differential equations in theory, but in the real life you cannot go to infinity. So you have a system like that. So you have the equation before, the biochemical equation. This is what you learned before. So you will learn that next week. How you proceed. So here there is some overflow. And then, so just to finish with one theorem at the end, so you look to the moment of the mass, the mass, and then you close your system, and just because I'm a mathematician, I want to finish with one theorem. So you see, it's a complete problem, but at the end, we succeed to do some mathematics. So it's not so important. What does it mean the second number goes to infinity? No, but there is a consequence in terms of medicine. What does it mean? So it means you have a gel. So what is a gel? It means you have something that you cannot break. So you have like a gate. Some will be broken, but there is still a gel, something that cannot be broken, natural. Or maybe you have to use medicine to try to break this gel. So even if it's very theoretical, this is important in terms of medicine. So I will not explain that, so because this is also the lecture of Annabelle, but you can have a treatment, so you can combine what happened with one treatment. So this is the G. With another treatment, what happened when you combine the treatment. So all of these are available. So I don't tell you what are the treatment because it's still confidential. But this is the kind of thing you can do. And I'm sure you will be able to do after that. Okay, so just take 2 minutes. So as a conclusion, so this is one example, but you will see with the slide, with the mini project. So mathematics, so you can. So here, totally about oncology. So in oncology, you have so many things in mathematics to do. So some very practical. Something very fundamental, so you can do mathematics, but also fundamental in terms of biology. So the biology on the back is very short. So here, in our case, so with the help of mathematics and help also of the medical, we highlight the coagulation. So this is something very important. People didn't know. So and why the coagulation is very important is that so because you have this aggregate, so the medicine cannot work like the gate. So you can provide any drugs, it doesn't work. So even in immunotherapy, it doesn't work. So this is something very important for the surgery. So because at the end, this goes back to the surgery. So the guy who will operate, he knows that. Actually, he knows that before, but now he's sure. But yeah, you need to be careful, depending on the patient. Okay, so as I told you, so now it's almost mandatory to have in silico, so that's why it's important for you to be schooled. So because in the future, everywhere in the world, they will ask this part repeatedly. So of course we will not avoid in vivo tests, it's almost impossible, but always we say we still have to test it on animals, on humans, but you can reduce the number of badly treated animals. So this is very important. So just to show you can think about that later, you can see. So this is the guideline from the FDA. So I told you, FDA imposed now in silico trial, you have to follow all of this. And all of this is exactly the topic of the school. But as Gideon told you, we proposed this school 2 years ago. So before the FDA said you have to. So we are in the good way. It's available. Okay, so thank you very much. I hope you will.